Okay, because of the work we're going to be doing with exponents, there are a few things that you should memorize. So jot these down. And some of you might be like, Miss Collier, I know those already. Awesome. But you want to know that 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, and 2 to the 5th is 32. These just come up so frequently that having them memorized will be helpful. 3 squared, 9. 3 cubed, 27. 3 to the 4th, 81. 4 squared, 16. 4 cubed, 64. All right. So if you would commit those to memory, that will help you out a lot in our work on exponents. Alright, so what we're going to do now is talk about taking exponential equations and converting them to logarithmic equations and going back and forth between that. And the idea that I want to start with is something that you did back in the first grade. The idea of a fact family. And back in first grade, fact family went like this. 2 plus 3 equals 5, right? That's an addition sentence. And it goes with the other addition sentence, 3 plus 2 equals 5. So we learned very early on that addition is commutative. But then we learn an associated subtraction equation. So we learn that 5 minus 2 is equal to 3, and 5 minus 3 is equal to 2. And so we say that these mathematical sentences make a fact family because they are related to each other. Okay? Subtraction is the inverse of addition. Addition is the inverse of subtraction. So the same type of relationship happens with exponents and logarithms. So if I have the exponential function 3 to the 4th is equal to 81, that's an exponential sentence. The log sentence that goes with it says log base 3 of 81 is equal to 4. And the way that we read this, I'm going to put it in quotes because it's what you would say. We would say log base 3 of 81 equals 4. So in our exponential equation, the number 3 is the base. We talked about that last time. And in our logarithmic equation, the number right there is the base. So when you are converting from exponential to log or log to exponent, if you just remember, the base is the base. The base is the base. That's the secret formula. Alright, so if I have 2 to the 5th is equal to 32, and I want to write the logarithmic sentence that goes with that, I write log base 2, because the base is the base. So the 2 and the 2. Now, what's on the right-hand side of the equals is it can't stay the same, right? That part's got to change around. So it's got to be equal to 5 instead of 32. So it's log base 2 of 32 equals 5. But if you anchor the base down, then the other ones you just plop them into place, and there you have it. Make sense? Remember it from last year? Kind of, sort of, maybe? Alright, there are two special bases for us to talk about. The common logarithm is base 10. So when we're dealing with base 10, a lot of times we just omit the base completely. So log base 10 of x is often just written as the log of x. So when there's no base there, and you're like, Miss Collier, the base is missing, it's understood to be base 10. So the common logarithm is base 10. You don't see a base written there, it means base 10. Alright, then our other logarithm is the natural logarithm. And that is base e. E is a number. And so when we have a logarithm to base e, it would look like this. Log base e of x. But we're actually never going to write that. That's what we're thinking inside of our brain, but we don't write that down. Instead, we write ln. ln stands for natural log. So it would be the natural log of x. But when you see an ln in your brain, you can think log base e. So let's think about how we would change a natural log into an exponent. So if I had the equation y equals the natural log of x, so in my brain I'm thinking y equals log base e of x. Natural log is base e. So then I'm thinking the base is the base. So I put e to the y power equals x. So that's the equivalent exponential sentence that would go with that logarithm sentence. And we'll talk more about natural logs later.